Hello, guys. Once again, we are going to work on a free response problem. This one is a little more conceptual, not so much algebra, but um, what we want to study is how forces act on a particle and how they affect exactly the acceleration and the velocity of that particle. So let's go there and see what they describe for us. What we have here is a pendulum, and they tell you specifically that you have a heavy ball that swings from end to end tied to a string, and they want you to neglect air resistance. Point P is the lowest point in the trajectory. Point Q is one of the two endpoints or highest points. And so this pendulum has several situations along its motion. This is a real life demonstration of what the pendulum is doing. Notice how the direction of the motion is changing. Of course, the path is part of a circle. Also notice that the velocity is changing. In particular, the velocity at the end points of the motion is zero. And you also have periods of increasing and decreasing velocity. It is also a matter of theory that because it is changing in direction, there is acceleration on this motion. In particular, they want you to analyze this. On the following diagrams, draw and label vectors that could represent the velocity and acceleration of the ball at points P and Q. First of all, it's very important that you understand how to follow the instructions to the letter. They want you to draw and label vectors. So it's not enough that you draw them. You also have to name the things in writing. That's what labeling means. Even if you draw it correctly and you don't have a proper label for it, you probably won't get the highest possible grade. Now, what are you expected to draw and label? Well, they just said it's vectors that could represent velocity and acceleration of the ball. So here we are going to use a code where red is velocity and purple is acceleration. In the test, you probably won't need that. Pencil is more than enough, but it's important that you understand that you are drawing two different vectors of two different kinds in each case. It also says that if a vector is zero, take care that you have to explicitly say it. It's not enough that you don't draw it, you have to say that you know that the vector is zero. And finally, that these dashed lines represent horizontal and vertical positions. So, if you look at the pendulum, at point P, you can see that this is the point where the ball is going to go fastest and it's moving directly to the right. So that's what you're expected to draw at this point. A horizontal vector, we are going to name it the velocity at P, and this vector, another thing that you might be aware of is that this is the maximum that you can have, okay? In the time before passing through point B, the velocity has been increasing, and then after that, the velocity has been decreasing to zero. So this is the maximum velocity at point P. If this is the maximum velocity, this is the point where the velocity has stopped growing and it started decreasing. Therefore, at that point, dv dt is equal to zero. But this is the same as saying that the tangential acceleration is zero. What we are trying to say in that case is that at P, there is no change in the magnitude of the velocity vector. So, If there is no change in the magnitude, what about the direction? Well, just like the figure indicates, the object is always following a circular path. And so it is changing direction. The velocity is changing direction all the time. In particular, this means that you do have an acceleration, and this is what we call a radial or centripetal acceleration, because you do have a change in the direction of B. Now, this centripetal acceleration is along the radius of the circular path, and so this will be the acceleration at point P. Notice how the acceleration is completely perpendicular to the velocity, which is always what causes the velocity to change direction. So that is the motion vectors of the ball at point P. What happens at point Q, which is one of the endpoints where the ball momentarily stops? At point Q, it is important to see that this ball has just stopped moving to the right, and it is barely starting to move to the left. So what can we say about the velocity at point Q? Precisely that the velocity at point Q is 0. This is only an instantaneous situation. The velocity is only 0 at this particular instant, but it is 0, okay? And also, you want to say what happens with the acceleration. Now that's a little trickier, because in that case, it's best to consider a free body diagram to see what's going on with the forces at that position. So we want to say that x is an axis that is perfectly tangential to the circular path. Y is radial along the string. And so for these two axes, what you can say about the forces is, first, that there are two of them. One of them is the gravitational force, mass times acceleration due to gravity. The other one is the tension along the string. Now, because you have a vertical weight and the y-axis is inclined, there is an angle theta between the y-axis and the weight, which basically is telling you that you have two components. The y component, because it's the adjacent side, is mg cosine of the angle. The x component, because it's the opposite side, is mg sine of the angle, and depending on your standards, you could say that this is a negative mg sine of the angle. Now, what matters here is that there are two forces that are opposite in the y direction, and so the net force in the y direction is 0, because in the end, there is no acceleration at this point that is either going to shorten the string or to lengthen the string. The radius is fixed, so the tension and the y component of the weight cancel each other out. Not so in the x direction. In the x direction, you only have one force. So in that case, mass times acceleration is equal to the net force in the x direction, which means mass times acceleration is negative mg sine of theta. So your acceleration is negative g sine of theta. The important part is that this is along the x-axis, and we just said that the x-axis is tangent to the circular path. So what we are saying is that we have a perfectly tangential acceleration at point Q. This is completely tangent, which means it is at 90 degrees with your string. So in this case, you could say the following, that there is only change in the magnitude of the velocity, but, and here is another controversial thing, there is no change in the direction of the velocity. Or in other words, what this is saying is the centripetal acceleration has to be zero. Now, we have to support that claim, but it's relatively easy because if you remember, the centripetal acceleration has a magnitude that depends directly on the speed. It's the square of the speed divided by the radius, but the speed is zero here. So you have zero divided by the radius. There is no centripetal acceleration, only tangential acceleration that is pulling the ball towards the center or towards point P in this case. So the velocity is zero, the acceleration is only tangential towards the midpoint. Now, the next is a what if question. And what they want you to say is, what happens if the string breaks? So let's go there. See what they tell you about it. Consider that you can neglect the resistance, the mass of the string. The important part is that the string breaks, and the string breaks depending on what they are asking at point P or at point Q. Now, what are they requesting you to consider? They want you to think about the path of the ball depending on where the break occurs. So let's go with point P. When you were at point P, remember, the velocity was completely horizontal. That was the velocity at P, and now the string just braked. And so if you have no longer any tension force, then there is only one force acting on this object, which is the gravitational force mg. This means that you have only gravitational acceleration negative g. So you have constant velocity in the x direction and accelerated motion in the y direction. Basically, this is a projectile. You could say that the path that this object is going to follow has to be a parabolic path like this. And so there are several ways in which you can fulfill the question that they ask you. Remember, they want you to briefly describe the motion. You could say, for example, that the ball moves as a projectile, or more specifically, you could say the ball shows constant velocity in x and accelerated motion in y. And there are several other ways in which you can describe this, but they all have to be equivalent, okay? Here you can see an emulation of what is going on when the string breaks at the midpoint. In slow motion, it is very clear that the projectile actually follows a parabolic trajectory. Finally, they want you to consider exactly the same question. How does this object move if the break occurs at point Q? Now you want to remember that at point Q, the speed was 0. So at point Q, this is what we have. Originally, there is no velocity because the speed at Q was 0. The object is momentarily at rest. And now the string breaks. And if the string breaks, then you can say something that is very uncontroversial, and is that the only force acting is the gravitational force, and therefore the acceleration of this ball is exactly downward and it starts from rest. So your motion has to be free fall motion. One way in which you can describe this graphically is by showing arrows that are separating more and more, like this, or you could simply say the ball falls freely. You could also say the ball starts from rest and accelerates downward due to gravity. Once again, there are several different ways in which you can describe the motion, but you do have to give some kind of written description. And so this is it, guys. What you are expected to do is simply to give qualitative arguments to say how these forces affect both the velocity and the acceleration of this particle. So I hope this is useful for your conceptual development, and I'll see you next week with another free response. Thank you for your attention.